Everyone, it's our pleasure to have Professor Rob Knox from the University of Wisconsin-Madison. He holds the Keaton Nosbusch Professorship, and I pronounce it
That's right.
correctly,
Yeah.
nice,
Yeah.
of Electrical and Computer Engineering at the University of Wisconsin. He also runs a center, Air Force Center on data science, machine learning, which we deal with lots of different people participating, lots of research funding. And he's received tons of awards, including Signal Processing Society Best Paper Award 10 years ago now, I think, and lots of citations because Rob's papers are so wonderful to read. He makes things clear, and yet they're deep and fundamental and interesting. So we're very happy to have you here today, and we'll be talking about deep learning and sparse regularization. So let's welcome our speaker.
Okay. Thanks, Laura, for that nice introduction, and thanks for the invitation
Do you
to
want to
visit.
check the microphone? Is it on or?
The light looks on. Yeah, okay. Yeah, if anybody on Zoom can't hear me, they can let us know somehow. But anyway, yeah, it's great to be here. It's been a little while. There was a whole pandemic thing and so forth that shut a lot of visits down, but it's great to be back. Yeah, I'll just get started. So some of those awards that Laura mentioned had to do with sparse signal processing. And so what I'll talk about today is some work that we've been doing over the last few years. It started off with Rahul Pari, who's a former PhD student who's now in Michael Unzer's lab as a postdoc at EPFL, and then two of my current PhD students, Lou Yang and Joe Shinuda. And what happened is Rahul said, I really want to work on wavelets and that sort of stuff. I'm like, yeah, I don't know exactly what the cool open problems are there. Why don't we see if we get, so we wanted to do functional analysis. I said, well, let's try to see what we could do in deep learning. And so we kind of got started down this path, and it actually ends up connecting with all sorts of things I did in the past. So it's been really fun, and it's still ongoing. So I'll kind of tell you what we've been up to. So let's see here. I think I just have to, how do I get other, or maybe I just have to touch this. So I was going to start off with a brief and personal history of neural networks. So I did not, this is not the first time I thought about neural networks. For the older people in the audience, you may recall that in the late 80s, there was a lot of excitement about neural networks. And it was there was that excitement was really generated by a paper by Rummelauer, Hinton, and Williams on backpropagation. See, how do I do this? Yeah, there we go. And so at the time near that, I was working at G Medical Systems. I was supervised by a woman named Ann Hall. And somehow I said I wanted to do something with neural networks. And she had some collaborations with people that were sort of kind of optimizing, kind of viewing of CT images. How do you get the window and level set just right so radiologists can read them very easily? And I used neural networks to kind of explore that, and they worked super well. And I'll just say what happened is I had this neural network solution. It was beautiful. It worked better than everything else. And then Anne said to me, "That's great, Rob, but why do they work? Or why does it work? How does it work?" And I had no answer for her, but it really was kind of a profound kind of moment for me, because I thought, wow, that is the right question. Not so much that they do work, but why do they work? How are they working? And that stuck with me. And then I tried to explore that question a little bit in an area that I was very familiar with and thought I understood well, which was like image edge detection and basic image analysis. And then I did this master's thesis project thing on that a year later. I made a little progress there, but what happened then is things started to change in the research community. There was a really important paper by Andrew Barron in 1993. And really what this paper said is he introduced this really interesting class of functions, d-dimensional multivariate functions that can be very well approximated by neural networks. Basically, a neural network with n neurons could approximate functions in this very big function class with an error that goes down like 1 over the square root of the number of neurons. And that was kind of shocking and amazing, because usually when we think about multidimensional function approximation, we suffer from the curse of dimensionality, that if I had n neurons or n building blocks in my way I'm building my functions, say n sinusoids, for example, we would expect maybe the approximation error would go down like n to the -1 over dimension, so very slowly. But there was something interesting going on with these function spaces that Barron introduced, and we'll come back to those today. They connect with what I'm going to talk about too. So that was really great, and somehow we were making a little progress understanding neural networks here. But then what was going on at the same time is people started thinking about other things like support vector machines and wavelet methods. And both of these had kind of a more tractable mathematical structure to them. And people largely left neural networks for a while and focused on things like kernel machines and wavelet methods and so forth. And I did as well. So I left neural networks at that point in the early 90s. And here we are today. GPT-4, everybody knows about it. And just yesterday or the day before, some people, because we don't understand these systems, they're really sort of alarmists, and they're saying, well, let's just stop. They say this, they say, well, like, look, these are very powerful. We don't understand them. There's risks and whatever. So we are calling on all labs to pause the development of these systems that are more powerful than GPT-4. I have no idea what that means by more powerful, but we should just stop for 6 months. So these are, fear mongering, I think, a little bit, and probably pretty naive. Nobody's going to stop. So, but I think the motivation for this open letter is that we don't understand these systems well. So I'll talk a little bit about how I'm trying to understand at least parts of them and how they're working. All right, so here are modern neural network architectures, a ConvNet and a transformer. Of course, GPT-4 is based on transformers. And there are a couple of things that are very kind of common across many architectures that turn out to play an important role. And those are, they use a common activation function called the rectified linear unit. It just basically takes whatever the input is and outputs the positive part, sets the negative part to 0. So that's the ReLU. I'm sure most people are familiar. And then there's also often a kind of regularization used in the training of neural networks called weight decay. And it turns out that these two simple ingredients lead to some very remarkable properties and give us lead to some deep insights into how neural networks are functioning. Okay, so this is sort of what those two things together do in a nutshell. And I'll kind of go over this a few times and explain it a little bit more detailed. But here's a neuron. So a neuron takes an input X, weights X by W, and then has some output of the neuron. And then that output is weighted by whatever the output weights are. So W are the input weights, V are the output weights. This is a neuron that has multiple inputs and multiple outputs. And we can write the rectified linear unit like this, where we just, again, take the inner product between the input weight vector and the input to the neuron X, take the positive part, that's what that plus means, and then multiply by the output weights. And weight decay in training, if you have a neuron like this in your big neural network, there's going to be a term in your training process that is basically regularizing the sum of squares of the input and output weights, the V and W there. And what happens is that if you train a neural network with weight decay, then at a solution to the minimization problem that you're trying to solve, the two norms of the input and output weights to every single ReLU neuron are going to be exactly balanced. They're going to turn out to have the same norms. And that is sort of one key kind of observation that leads to all sorts of insights and conclusions. So we'll talk more about this, but this is what we call neural balance, and I'll show you why this actually happens. It's pretty straightforward to see. Okay, so to begin, let's just think about training neural networks. How does this work? So here's a shallow neural network. I have a bunch of input weight vectors and output weight vectors. We're going to be using the rectified linear unit. I'll use these kind of orange nodes to denote the ReLUs. And then we can write the function that the neural network is representing like this. Again, it's just taking the inputs inner products with the input weights, positive part, weighting by the output weights, and then summing up all those neurons' effects. So that gives us a function. The kind of optimization that we'd be trying to solve when we train a neural network would be something like this. I'm going to look at squared error here, but it could be any other of your favorite loss functions. So this is sum of squared errors. That's your data fitting term. And then a regularization term. Again, the regularization that corresponds to what people call weight decay would be just the sum of squared weight, something proportional to the sum of squared weights in your neural network. And then gradient descent is how we would train. I'm just showing the gradient descent update for an output weight V sub j. But basically, what's going on is you could think of it as having two terms. One is the gradient descent on the loss function, and then the other is the gradient descent term coming from the regularizer. And this second term is what they call weight decay, because it's sort of shrinking the weights a little bit at every iteration of the gradient descent. Okay. So that is what people call weight decay. It's just what you might call sum of squared weights regularization or ridge regularization. Okay, so this is the standard approach to training neural networks, possibly with a different loss function, not necessarily sum of squared errors. And here's why we get this neural balance that I talked about before. So because this rectified linear unit is piecewise linear, it's easy to see that we could take a neuron and we could multiply the input weight by some positive scalar alpha and correspondingly multiply the output weight by 1 over alpha, and that will not change the overall input-output mapping of that neuron. And that's, again, just because the ReLU is piecewise linear. And so because of this, we have this balance that the input and output weights will be equalized at a global minimum of the weight decay objective, that training objective we were just looking at. And that's because maybe I'll just go back to it really quickly just so you can see, but here, if I scale the input and output weight, as we were just talking about, that won't change the data fitting term at all. The data fitting term is invariant to that scaling with that alpha I was just talking about. But the regularizer is not invariant to that scaling. In fact, the regularizer, that's what I'm saying right here, would prefer to have alpha set in a way that just balances those terms. It doesn't make sense to have the sum of squared input weights much smaller than the sum of squared output weights, or vice versa. It makes sense if you want to minimize that overall objective that they're exactly balanced. So that's all that's going on. Very simple. And that leads to this balancing kind of condition. So at a global minimum of the weight decay training objective, the sum of squared weights is equal to the product of the norms of the input and output weights because of this balancing condition. Okay. So, and this is something that kind of has been known for a while. This is the first appearance of this observation in literature, a paper by Granville in '98. And then some people at PTIC in Chicago kind of rediscovered it and kind of put it in the context of modern deep learning systems. Okay. So this leads to something that I like to call the secret sparsity of weight decay. So normally when we have a regularizer that's sum of squared weights, we don't think that that has anything to do with sparsity. It's just kind of trying to make all the weights small, maybe kind of in a fairly uniform way, but in fact, it leads to some sparsification of neural networks. So this is the original weight decay training objective, loss function plus sum of squared weights. But if we go here, why am I stalled again? Oh, there it comes, okay. So at a global minimum, I just showed you that the sum of squared weights is going to be equal to the sum of the products of the two norms of the input and output weights. So what that tells us is that these two optimization functions, while they're different optimization surfaces, they have the same global minima. So we could have, instead of using this objective, we could have tried to minimize this objective, and we can, kind of take that one step further. We could actually absorb all of the scaling of the neuron into the output weights. So we could just constrain the input weights to have unit norm and then just solve this optimization. So all three of these optimizations have the same global minimum. That's the claim here and the fact. And if you look at this term, which is the sum of the two norms of the output weights, that just looks like a group lasso type regularizer on the output weights of the neural network. Does that make sense, everybody? And so we know that things like group lasso will lead to sparsification. If we solve an optimization like this, typically some of the V's are going to end up being exactly the zero vector. And if we were in a case where this is sort of the multi-output case where the neurons have multiple outputs, but if we had just a scalar output, this would just be the L1 norm of the output weights. So it would really just be the lasso. So let's look at this. So here I'm looking at a really simple data fitting problem. The blue dots are some data points. This is just a univariate kind of function. I'm training a ReLU neural network with 320 neurons in it, and we only have 32 data points here. So we're kind of in this so-called over-parameterized setting. We have way more weights in our model than we have data points. And the two kind of curves or functions you see up there are two different neural networks fit to that data, roughly doing the same thing. There's not a very interesting function here, but what was happening is I was training a neural network with just the usual weight decay, gradient descent with that weight decay term that we talked about before. And what happens is, if you look at how the neural network is fitting the data, very quickly it fits the data perfectly or nearly perfectly, and it just kind of stays at that data fitting level. But if you keep iterating the gradient descent SGD longer and longer and longer, the network keeps changing and it actually gets sparser and sparser and sparser. It starts off with 320 neurons that have significant weights. They're all initialized to some random values, but eventually most of those weights tend to effectively zero, and there's only 12 neurons left that have any significant kind of weights in this particular training. Another thing you do is, as you just saw, an equivalent optimization would be this lasso or group lasso. So instead of using gradient descent with weight decay, you can use proximal gradient descent, where you actually use a proximal step, which is soft thresholding in this case, to implement that other regularizer. And you'll get the same sort of thing. The data fitting, I didn't even change it. It looks exactly the same. It quickly goes to zero. But if you look at the sparsity level, this is the number of neurons that are sort of surviving after a certain number of training steps, it quickly kind of reaches this sparse level of 12, much faster than the usual gradient descent with weight decay training. And so what this is sort of showing us is that, you know, if you keep training longer past the point where you're fitting your data well, neural networks will tend to get sparser if you're using weight decay. But there are also ways to accelerate that whole process and reach that sort of limiting condition of a very sparse solution using alternative training methods like proximal gradient descent. Okay. Any question on this example? Yeah.
So I think sometimes we say that early stopping improves generalization.
Yeah.
Isn't it like doing the contrary of?
Yes, yeah. So here, this is sort of saying if we don't stop early, if we just kept going forever, what happens? That may or may not be a good final solution if we're interested in generalization. Usually we would maybe have another held out validation set. We'd be monitoring the accuracy on that set and then stopping when we see that accuracy goes up and it starts to go down, we'll stop there. So that's another form of regularization, early stopping. And I guess you know, all these things kind of could be working together a little bit. So I'm not making any claim that this is maybe the best way to get good generalization, but there's a lot of work out there and papers out there where people say that, oh yeah, you know, adding weight decay definitely helps with generalization. There's empirical evidence and, you know, theoretical reasons why this might be, but early stopping is another thing that would be maybe important practice. Was there another question over here?
Yeah. How do you maintain the unit norm W's in this training?
Yeah, so that you can implement as also a proc step where so if I just maybe go back to that, just so we can look at it, so this, you can just think of, there's a projection every time onto, that's sort of the proximal operator for this constraint. So you'd be projecting the input weights onto the unit sphere. And then this one is going to be the shrinkage kind of thing. Question?
Yeah, I was just a little confused. So this is the L1 regularization, but I don't see any L1 terms. Is this?
So yeah, sorry. If you had a scalar output neural network, these would just be scalars, and this 2 norm would just become the absolute value of each output weight of each neuron. And then this would just look like an L1 norm. So this is sort of the L1 norm, if you will, of the 2 norms of the vector. So I'm just kind of using that term L1 loosely. This is sort of like an L1 norm, even in the vector case. You can kind of think of it as having the same kind of lasso-like behavior. But if it was just a scalar output neural network, then that would exactly just be the L1 norm. Thanks for that clarification question.
Yeah.
Does that make sense then? Yeah, cool. All right, so, oh yeah, here's a little movie just to show what's happening in 2 dimensions. And the best way to see this is to just, oops, where am I here? Let me do that again if I can pause this somehow. Okay, yeah, pause this one and maybe move it back to about, so there's the same place, like right around 1 second and right around 1 second. So at the top, I'm using this proximal gradient descent, and on the bottom, just normal weight decay. And just visually, you could see here, oh yeah, this one's keep getting to finding the decision boundary faster than the lower one. So yeah, this is just another way to visualize it. Oh yeah, if you do something a little different, you'll end up with the same solutions, or again, I shouldn't say exactly the same, but they're going to be roughly both solutions to the same kind of optimization problem, but the proximal gradient is going to be much faster.
Rob, this is a decision boundary. So you're using mean square error loss for a classification problem here?
This one would be using like logistic regression loss. Yeah, so you can swap out, it doesn't really matter what loss function you use there for this kind of thing, because the whole loss, whatever it is, will be invariant to this rescaling of input and output weight. So this was a classification problem with logistic loss. All right, so so we talked about this neural balance theorem. Here's VGG16 architecture. There are lots of ReLU units in this deep neural network architecture. And again, what neural balance would say is that if you really train this with weight decay and you train it to find a global minima, or if you can find a global minima, what must happen then is that all the input and output weights of each ReLU must be equalized. And so we tried, training VGG16, either using normal weight decay training or this proximal gradient method. And you can see over here, this column, these are like, accuracies and so forth. In a number of cases, it actually does end up not only being faster, but giving a slightly better generalization. So to answer your question, I don't know if this is the best way to get the best accuracy at test time, but in fact, it actually seems to help sometimes to use these types of methods. And there's been a lot of work. I think even Laura's done some work on sparsifying neural networks with different kinds of sparsifying types of regularizers. I'm not sure exactly which ones and which papers we're comparing to here, but these are some of the standard things people who do, group lasso, which are a little different than what we're doing versus this kind of prox operator that I was just talking about. And here I'm looking at test accuracy versus the number of neurons that remain. As you increase regularization, you're going to be getting a sparser and sparser neural network. And you can see here we're actually doing quite well in terms of accuracy versus sparsity trade-off. And so I think what's kind of interesting about this is that we're not really proposing to do anything new. We're just proposing to train for what we think should be the solutions to normal weight decay training a little differently. And that actually seems to be a great way to do sparsification of neural networks too. Okay. So now I want to kind of say a little bit about what does this tell us about what kinds of functions neural networks are learning. And to do that, we're just going to, first of all, look at a shallow neural network with just a scalar output. So again, in this case, then the output weights will just be scalars, and that norm we were talking about would just be the L1 norm. And we, again, have these two optimizations are equivalent to each other, the normal weight decay objective function, and then this one with this product of the absolute values of the output weights and the norms of the input weights. And that's what people sometimes call the path norm of a neural network. Okay, this regularizer here, they would call that the path norm of a neural network. And so we could think about the space of all functions we can build with shallow neural networks like that. So I'm kind of writing out the space here. So take whatever weights you are, take however many neurons you want to have. And you can say, okay, well, that gives us a space of functions. What is that space of functions? How can we understand it? This path norm actually gives you a valid norm on the space of neural network functions. So this space script F is a function space. If I identify each function with its neural network representation, then that gives me a norm on this space. And then you can complete this space with respect to that norm. That gives you a Banach space. And you can think about, well, what is then this completion? It's all neural networks that look like what I have up there, plus sort of their limits, which we could then start writing in this integral form. So what is this integral saying? It's saying take input weight vectors that are unit norms, so on the unit sphere. Then you have your neuron, and then this measure right here is playing the role of the output weights. Okay, and so this kind of integral representation, sometimes called the continuum width model of a neural network, is what was going on in Barron's paper. He was talking about something like this, and there's a nice paper by Francis Bach that also looks at this, and he called it convex neural networks because it's convex in this measure nu that you have here. Okay, so we can actually relate that norm. It's doing something, what is it doing? What is that norm that I was just showing you? Well, it's related to the second derivatives of your function. So we can see this by just looking at a very simple function. So this function f is composed of 3 ReLUs. And where each one turns on, you have a change in the slope of this function. So those are the weights and biases of your neurons give you this piecewise linear function. So that's a function. If I take the first derivative of that function, piecewise linear function gives me piecewise constant derivative, where the heights of each piece are equal to the slopes of each line in that piecewise linear function. And then if I take the second derivative of that, I'll get a bunch of Dirac impulses. And the Diracs are just going to be the kind of heights of the jumps between each piecewise constant area of that function. And so what this is showing is that, so these heights of these Diracs are exactly what that path norm was in this case. So the path norm of your function is the sum of the products of the weights, the magnitudes of those, which is just basically, it looks like the integral of the absolute value of the second derivative of your function. We have to be a little careful because actually we can't take the integral of Diracs, but technically, this is what's called the total variation. Right? I don't know what's something's down there. Maybe just locking a little bit. I don't see it on my computer, but whatever. It doesn't matter. I think it's fine. So what this says here is this the total variation of the first derivative. So if you say what's the total variation of this function, it's just counting up and adding up the sizes of the jumps. Okay. So this sort of shows how this path norm is actually regularizing something about the derivatives or the smoothness of your function. And so we can think about it this way. We can say, okay, well, we had the weight decay objective. We said that's equivalent to this kind of L1 regularization, which we could also think about as being equivalent to this total variation regularization. So we have our data fitting term, we have our function here, and what these regularizers are really doing is regularizing the total variation of the derivative of the function. This is sometimes called the second order total variation of the function. All right. And this is a function space. This is not a new thing. People have studied this. It's called BV2, bounded variation 2, or second order bounded variation. It's the space of all functions with total variation of the derivative being bounded. And another way that this is written in mathematics is the measure theoretic total variation of the second derivative, which again is just counting up the magnitudes of those Dirac impulses. Okay, so what Rahul and I did is we were able to use this kind of observation to say something about what kinds of functions neural networks actually learn when they're fit to data. And so here I just have, so what we're going to do is we're going to say, okay, suppose that we have any data set, and maybe we're going to try to do this. We're going to take a loss function. We're going to try to fit our data with a function from this function space BV2. We're going to use that total variation, second order total variation as our regularizer. And it turns out that if you do this, so this is an optimization over an infinite dimensional Banach space, but if you do this, the solutions there are solutions that are sparse neural networks that are exactly neural networks with rectified linear units. So let me just kind of point out a few of the things here. So you have the ReLU neurons pop out. You have this affine term, which is what in neural networks are called skip connections. And then it's sparse. The number of neurons that you're going to have in this kind of solution are going to be less than the number of data points in your training set. So this is kind of telling us that ReLU neural networks with skip connections are actually optimal solutions to these infinite dimensional function space problems. And so what's going on here? How do you see this? I'll just kind of give you a high level story about it. So the second order total variation is defined in terms of the second derivative operator. And the Green's functions of the second derivative, ReLUs are Green's functions, and the second derivative operator has a null space. That's all the linear functions. So that's why we have the affine term. That's the part that's in the null space of this operator. Any function in BV2 can be expressed in terms of a finite measure. So here I'm taking the second derivatives of a function. I can associate that with a measure nu. And then if we're trying to say, well, what we want to minimize the total variation of the measure subject to linear constraints. The linear constraints are our n data fitting constraints that we're trying to satisfy. This turns out to be equivalent to something called the measure recovery problem, which was studied in the last century a long time ago. And it's been known since then that the solution is a sum of Diracs. And then you're just going to take the pseudo inverse of that differential operator, applied to each Dirac, you get a ReLU activation function, so the Green's functions, and then that gives you this form. So those are sort of the ingredients of how you prove that solutions to that function space optimization problem are actually neural networks. Okay, so this can all be generalized to multidimensional cases too. And this was some great work by Greg Anji, who was actually Laura's postdoc. Then he went and did a postdoc with Rebecca Willett too. And he had this great insight. He said, well, if we want to extend that idea to multidimensional neural networks, we have to use the Radon transform. So let me just show you how that works here. So here I'm showing you a neural network with 7 ReLU neurons in it. So it's a piecewise linear surface. I'm going to take second derivatives, the Laplacian of that. And what I'm showing you is sort of a top-down look at the function, and the blue lines are the activations, boundaries or thresholds of each neuron. But once I take the second derivative, everything where it's linear gets wiped out, and you're just left with what you can think of as sort of like lines or Dirac lines everywhere you had one of these activation thresholds of a neuron. And then if you project lines, you basically get impulses. So this is now the filtered Radon transform domain picture. You get one impulse for every neuron, every activation threshold, and the kind of magnitudes of each of those Dirac impulses are equal to these path norm terms. And so what this is telling us is that the path norm of a function, which again is the sum of these products, we can think of that as kind of second order total variation in the Radon transform domain. Okay, so it gives us a way to think about what kinds of regularizations are we doing when we're doing weight decay? We're kind of effectively regularizing second order total variation in the Radon transform domain. So what Rahul and I did then is sort of say, okay, well, this also gives us a Banach space. It's what we call Radon BB2. It has those ingredients, the filter Radon transform, the Laplacian operator. It's the total variation of the second derivatives in the Radon domain. Essentially, what it's doing is it's measuring some sort of sparsity. It's an L1-like norm of second derivatives looking in every possible direction. That's what the Radon transform is doing, is kind of looking in all possible directions. And this is measuring how sparse are second derivatives when you just start looking in all different directions in this multivariate domain. And that gives us this RBP2 function space. So here we can use the same sort of machinery we just used before. We could say, okay, well, let's try to solve an optimization problem where we look at any possible function in this RBV2 function space. We want to fit our data, but we want to have a small Radon TV2 norm. The solutions to that optimization are also sparse neural networks. Same sort of structure. They have the ReLU neurons, they have the skip connections, and they're sparse. The number of neurons that you need is going to be less than the number of training points. And so this is saying that this infinite dimensional non-parametric training problem reduces to just training a finite dimensional neural network. It tells us kind of, how wide of a neural network do we need to make sure that going wider can't possibly improve our results. Yeah.
Basic clarification.
Yeah.
They're still doing two, like W and V, right? Not like a deeper network.
Yeah, here it's just, so for this, I'll say something about deeper, but for now it's just shallow neural networks.
But then like, what was the change when you went to Radon? It was the
That the
became higher.
the change is that the input, the inputs are, yeah, before it was just the inputs were scalars. It was just a univariate function. These are multivariate function spaces now. Yeah.
What is capital K?
Capital K is the number of neurons in the solution. So there are these sparse solutions to that problem. So it's basically like a representer theorem, similar to a reproducing kernel Hilbert space representer theorem, except that we don't actually know what the terms will be a priori, like we do in an RKHS. Okay, so let's see here. How am I doing on time? It's close till 10:15 or so, or 10.
20 minutes.
Yeah, good. Okay, so that's all great, but let me show you what this actually does. So I'm showing you, this is a function. Yellow is larger values, blue is, smaller or negative values. So think of that as like a couple of bumps. Suppose that we measure that function at some location. So the red locations, I'll measure the value of the function. And then from the measurements, the samples, I'm going to try to reconstruct the function. And I'm showing 3 different reconstructions from just measuring the function at those red locations. This is a thin plate spline, kind of the classical way you might do this. This is a neural tangent kernel. It's kind of a kernel approximation to neural networks. And then at the far right over there is the solution by fitting a ReLU neural network, training it with weight decay. And they all look good. That's all you're supposed to see here. They all did a pretty good job. Now let's look at a different function. This is a function that has like these ridges here. So it's constant in this direction, but it's varying in this direction. So this function kind of goes up and down like this. Okay. And we're going to sample it again at some random locations and then try to reconstruct. And here I've kind of played around with some of the bandwidth parameters in the thin plate spline and the neural tangent kernel to try to get the best results. This is the best I could do. And here's the ReLU neural network solution. And you can see that looks a lot better. Why does it look a lot better? So what's happening is that these kernel methods are what we call linear methods. They cannot adapt to this intrinsic low dimensional structure that we have in this situation. In this situation, we only have variation in the 45-degree direction, no variation at all in negative 45-degree direction. So it's kind of like a one-dimensional function, and somehow neural networks can discover that automatically. lock onto that and then do a much better job of recovering. Here it's sort of just saying, well, it's some multidimensional function. I'll try to get the function to fit where I have my data points, but it doesn't have the sparsifying property that allows us to kind of adapt to this low dimensional structure. Okay. So that's a picture. What mathematically what's going on. This is what goes back to this work of Andrew Barron that I mentioned. So you can kind of follow something similar to what Barron did back in '93. You could say, okay, if I have a function in this RBV2 space, how many neurons would I need to represent a function like that accurately? Well, it turns out that if you use m neurons, the approximation error in L2 would go down like 1/m. And then if you kind of do, this is just kind of hand wavy, you can make this all formal, but if you say, well, now if I'm trying to recover a function from observations, what will be my estimation error? You'll have an approximation error and a variance term. And if you balance those two out, you'll get this rate of 1/(n), where n is the number of samples that you've taken of that function. So the important thing is that's independent of the cursive dimensionality. The n to the -1/2 has nothing to do with the dimension of this domain of the function. Whereas if I did any linear method, like a thin plate spline or a reproducing kernel method or whatever, you would end up with a rate of n to the -3/d+3. So as d gets large, that's the dimension of the input space. It was 2 in the pictures we were looking at, but of course, nobody's working in 2-dimensional domains. We're looking at hundreds or thousands of dimensions. That's why these methods can, sometimes not work very well in those high dimensional spaces, whereas neural networks can, because they are able to kind of overcome this cursive dimensionality. They can lock in. And so this will be great if there is some low dimensional structure in your problem, it can learn it.
In the middle where you said balance those out, you mean by choosing the network width appropriately?
Yeah, in fact, we don't need to do that. It would all happen automatically. Often though, when we look at things like this, we would say, aha, well, how do I choose M to make this term over? But we don't actually have to do any kind of adjustment. You would want to choose your regularization somehow related to the noise level, if there's any noise at all in your problem. But usually we're not really that concerned with noise, more like just the fact that we only have a finite number of samples. So we're just going to use a little bit of regularization so that we essentially get a minimum norm interpolator in some sense. So here's a really kind of striking example. Again, that same 2-dimensional function, but instead of measuring it kind of all over the domain, suppose we just measured it at those red locations there. Then if we do the linear methods, they sort of will try to match what the function is doing. Where you've measured the function, they just kind of die off as you move away from where you've sampled. But the neural network will say, okay, well, I'll match what's going on where you measured it, but I'll also kind of just say, I think I could just represent that whole thing with a low dimensional model, and it will do this kind of amazing extrapolation, which could be good or bad. It depends what the function really looked like away from your samples, but it does something very different, right? It does something very different than linear methods. Okay. So in the last few minutes, I want to talk about now what happens with deep neural networks. Can we kind of get some insight there? So the first thing we have to do, because deep neural networks are sort of layers of neural networks on top of each other, we have to understand neural networks with multidimensional or vector valued outputs. So that's what I'm kind of depicting here. So we have a multidimensional input and a multidimensional output. For the same reasons we talked about before, we have these equivalent optimizations, or this group lasso type of optimization. And it turns out that this Latin group lasso type norm is a natural kind of norm that you would use for functions of this form. So let me kind of just write that down. This is mimicking what we just did before. So here's this optimization. I can look at these continuum with limits of neural networks and write them as an integral. And now we have a vector valued measure over there. That nu is vector valued. And the norm then of functions of this form will be the total variation of the L2 norm of that vector valued measure nu, which in the case of finite width neural networks just boils down to the sum of these two norms of the output weight vectors. okay? And what this tells us is that if we use weight decay in training, this is essentially what we're doing to our function. We're trying to find a function that fits our data, but makes this norm small. Okay, so this is the norm that weight decay is trying to minimize or regularize in terms of the function space, the functions that you're representing with the neural network. Okay, so here's a neural network. And you can say, well, what's the norm of this neural network? And what I want you to think about here is imagine that all the weights that I'm showing, which are the lines connecting these nodes here, input weights and output weights, just think of them all as being like some constant, like O1. So if each of those weights are some constants, then we can calculate this norm. And the norm of the neural network that we were just talking about would be proportional to the width of the neural network, which I'm calling W here, and then the square root of the number of outputs, which I'm calling D. Now, we already saw that weight decay is encouraging some sort of sparsity. So now let's look at a sparse neural network. So same number of neurons and so forth, but just now sparser connections. Again, think each weight or edge here is like a weight of order 1. This will have a norm of D, just the number of outputs. And then we can look at it even a different kind of thing, a structured sparsity, if you will. And in this case, these two networks have the same number of non-zero weights in them, but this one is more structured in its sparsity, and it turns out that has an even smaller norm. So what is this saying? It's saying that weight decay not only likes sparsity, but it really likes networks that share neurons. In other words, different output functions. So I have D output functions here, F1 through FD. It would be preferable if you can find a way to represent those functions where they share a lot of neurons together. So weight decay in training is really encouraging you to try to find or learn networks that look more like the one at the right there. So not just sparse, but structured sparse. Does that make sense? Okay. So deep neural networks are compositions of many shallow neural networks. You can define function spaces based on compositions of those vector value networks that I just talked about. You can define a regularizer then related to these function spaces. And you can also have a representer theorem like the one we looked at before, where now we look at one of these deep function spaces. We use this kind of deep version of Radon TB2 regularization. And the solutions to this will also be multi-layer ReLU neural networks. And what's in kind of one of the takeaways from this representer theorem is that the width of each layer, it's again going to be in some sense sparse. The width of each layer is going to be no more than, or can be no more than the number of training examples n times the output dimension d sub L of that layer. So whatever each layer has an output dimension. And so that's kind of telling us how wide layers have to be. It's a sufficient condition, but it might not be necessary. So that's why I kind of want to wrap up with. How can we use what we just talked about to understand how wide these layers and deep neural networks need to be? So the way we're going to do this, I'm just going to introduce a little bit of notation. So imagine I have n inputs to my neural network. I'm looking at some layer within that architecture. And at a particular layer, I have a bunch of ReLU neurons. And for each input that I put into my neural network, I get a pattern of neuron outputs, activation patterns, if you will, from coming out of each of those neurons. We're going to collect those all together into this big matrix phi. And then I'm going to take once I apply the output weights to those, then I get what's going into the next layer of the neural network. I'll call that the layer outputs, and I'll call that psi. I'll collect each of those. So now I have these two matrices. Each of them have n vectors in them, or n columns, corresponding to the outputs right out of the neurons. And then after you weight them by the output weights, the input to the next layer of neurons. So phi and psi. And we can kind of relate those. It's very simple, right? That the psi matrix is just going to be the output weights times the phi values. So I can write write that in that simple form. And what we just saw is that weight decay is trying to basically minimize the sum of squared weights subject to, of course, we have to match whatever we're actually observing in the neural network in terms of these, outputs of the neurons and the inputs to the next layer. And that's equivalent to a group lasso that's minimizing, again, the sum of two norms of the output weights subject to the input weights being unit norm and satisfying these equations. Okay, so here's kind of our layer width theorem. We have this matrices phi and psi. Then there exists, so you give me a neural network, it's trained up using weight decay. I look at these matrices phi and psi, and what we can show is that then there's a representation of the same layer with only k neurons, where k is less than or equal to the product of the ranks of those two matrices, which is always going to be less than the number of training examples and the output dimension of that layer. And why this is interesting is that it can be a really significant improvement over the bound we had before, and an improvement over the best known bound that was out there in the literature. And this often happens because in practice, as we go deeper and deeper in a neural network, the ranks of these matrices tend to get lower and lower. This is related to this so-called neural collapse phenomenon that people have observed empirically, and there's some theoretical support for it too. So let me just show you what this means, and I think I'm good on time, and I'm almost done. So here we're looking at VGG 19. Again, we're training on CFAR 10. We're looking at one of the final layers of ReLU neurons. In this case, the output dimension is 10, and because there's only 10 classes. And so what the theory says is that K, the number of neurons that you actually need, doesn't need to be 512. It would need to be no more than the rank of the post-activation matrix times the output matrix psi, which in this case happens to be about 10 by 10, so about 100. So the theory says that really you don't need 512 there. You can have an exactly equivalent neural network. It's going to agree exactly on the training data set, but it's only going to have 100 or fewer neurons. And in fact, we then took that neural network that's been pre-trained. We then ran a group lasso type of sparsification over it, if you will. And we found a new set of output weights that only, basically reduced from 512 to only 47 neurons. The training accuracy, basically they're agreeing perfectly on the training data, modulo kind of just, some numerical kind of difference there. But they're actually also, the sparser ones, doing just as well at test time too. So we preserve this neural network on the training data set. It might lead to a different function on new examples. We can't guarantee that, but the test accuracies actually are also preserved. So this is saying, like, a lot of things, like people have said, oh, let's sparsify while we're training, or let's do some ad hoc pruning of a neural network. We're saying you can actually prune in, you're not even changing anything. You can find a sparser representation of the same neural network. Okay, so I'm going to stop there. I'll just kind of wrap up what are the main points. ReLU neural networks are optimal solutions to data functions in these new function spaces, which are called these Radon bounded variation spaces. They have a lot of interesting properties: immunity to recursive dimensionality. Solutions tend to be sparse and narrow neural networks. They're adaptive to spatial and directional varying smoothness automatically. Weight decay promotes solutions that kind of like to have functions that maybe are intrinsically low dimensional. And by that, I mean, somehow in this high dimensional space, there's directions with strong variation, but most of the directions, there's little variation. That would be great for neural networks. And then this neural balance theorem kind of leads to new training algorithms, also new ways of pruning and sparsifying trained neural networks. And I'll stop there and happy to take questions. Thanks.
I saw a question in the chat pop up that asked you to explain neural collapse. They'd heard the term but didn't know what it meant.
Oh, so neural collapse means that, and I don't know, I mean, let me see if I can do this justice. So basically what the argument is there is that if you're using something like cross entropy minimization and you have, say, 10 output classes at the end of the day. What happens is you tend to get a situation where you have some sort of alignment of these weights so that, well, I'll just say roughly speaking, what's happening is you end up with just a very low dimensional kind of perfect representation where everything sort of, all the classes are clustered into just 10 nice compact little clusters or groups, which also would tell you that the weight matrices and so forth would be low rank. So there's some sort of idea that at the end of the deep neural network, you should have a perfect kind of representation of your classes where they just all collapse onto these sort of representative points. And then they're nicely separated and you just use a linear classifier to classify those. I don't know if there's a better short summary of what neural collapse is saying, but it's okay. Yeah. And so that would, if there's neural collapse happening, then that would also tell us that these matrices should be low rank in the deep layers of the neural network. And they are. There is some collapse sort of happening, usually. But what that's telling us is actually that we can find these sparser representations of these layers.
So when you were arguing here that, like on the table, that's the next thing that we could just use, we had as like with only 47 neurons, but you wouldn't know what that is until you train it in the first place and see the rank of the weight matrices.
Yeah, so this is, so here we just took a neural network that somebody else trained for CFAR10, this big neural network, and then we said, okay, well, let's look at the trained weight matrices, and it turned out that if I look at that post-activation set of that matrix, which I was calling phi, even though there are 512, this is a 512 by however many training pattern matrix, it's only about rank 10. Its rank is very low. And then, of course, these output weights are rank 10 because there's only 10 outputs. Its output dimension is only 10. So that's where the 10 by 10 comes from. So you can just observe that. That's what the trained network looks like. And so then that tells us right here that, well, we definitely don't need 512. If we want to just have the exact same function on the training data, there's another way to represent this layer with at most 100 neurons in it. And the only reason that these two numbers aren't exactly the same is because it's approximately rank 10. There's a tiny bit of energy beyond rank 10, but effectively exactly the same function on the training data.
So like maybe you would suggest like, okay, if you have the resources to train a wide network and do that first, but then if you need to implement it, you can have the same function for new test data on a cell phone or whatever, but that needs very like less memory and smaller.
Yeah, that would be one great application for this, is just reducing the size of a large neural network without sacrificing anything.
Right.
And the way to reduce it is it's just a nice convex optimizations at different layers. You can do them all separately. There's nothing really complicated going on. And instead of sort of like some ad hoc pruning or something else, and then hoping that you can, and we're just saying, no, you can look at what the ranks of these matrices are, and I can tell you, you can do it, you can reduce it without any degradation, at least on the training data.
Right.
It'll be exactly the same. Maybe I'll go to this guy here.
Yeah, so you're doing this on like the last hidden layer with the assumption that the layer before it has neural collapse, right? Which is why you can apply this.
Well, we're not necessarily assuming it. We can actually look at the trained network, and let me just kind of go what happens in this case is if I look at this phi matrix, which is all the output patterns that come right out of the ReLU layer here, I collect them into a big matrix. I can just check what is the rank of that matrix. And then,
My point, I guess, was like, so like, that the last one, last layer will be rank 10, and that's why you can apply this. So, but if you were to try to like fit, like, I guess sparsify like each layer, move back one at a time, like there would reach a point where you're not guaranteed it's rank 10, right?
Yeah, that's right. So here we know that definitely this matrix here is just going to be rank 10, right? This V matrix. But this idea of applying this group lasso, you don't need to know the ranks to apply it. You just won't know how sparse. So here, all we know is that we could get away with it most 100. In fact, 47 seems to be enough. That all this is just a bound. We don't know for sure if that bound's tight. Turns out only 47 were needed. So we could apply the approach without actually having to know or check what these ranks are. Right, and which would be good because you don't want to have to keep taking huge SVDs of huge matrices. So you can apply these group lasso sparsification methods. Again, what you'd be trying to do is exactly preserve what I was, let's see if I had it here. Yeah, maybe here, right? You want to basically say, I have a trained network. So I have, a bunch of relationships like this. This is what's coming out of the ReLU layer, and this is then what would be going into the next layer after you have those weights. So you have, in training examples, you have these N input-output constraints. You just want to say, can I find a new V matrix that's much sparser, that preserves exactly the same mappings? And so that you can do, you don't need to know what the rank of anything is to do that. Yeah.
So is the spatial adaptivity of neural networks something that become weaker as you increase the width? So from like an earlier figure, NTK seemed to not have any adaptivity to direction at all.
Yeah.
But then that is like an infinite limit. So is that something accurate, you would say? Or?
Yeah, so the NTK, it is a sort of infinite limit or infinite width neural network, but it's not really a neural network in the sense that it's still a completely linear model. It's just a kernel method. And so you can get that kind of limit under certain assumptions on, the training and so forth. But basically, you can think of it as training a neural network without trying very hard to actually train it. And then you get a different kind of limit that isn't really a neural network. It's a kernel method, and that will not have any ability to adapt to low dimensional structure. So neural tangent kernels don't have that property at all. They're one sort of limiting condition that training could converge to in a neural network problem, but I would just say that's actually not a neural network. It's something else. But if you really train a neural network, you will not reach the NTK limit. And so that's the difference between what they call, I'll call it real training versus lazy training. Yeah, so we could chat about that afterwards if you have more questions. Yeah. Anything else? Maybe I'll go over here.
For the representative theorem, you talk about deep networks. We know that Y is the role is playing for networks. So can your theory show some implication how the depth is playing?
Yeah, no. So I guess the question is like, if we looked at a deep neural network, how does depth show up in this story? Like, do we know anything about how deep or what the effects of depth are? And I would say no, not yet. I mean, it gives us some insight into what kinds of functions might be encouraged by training deep neural networks with weight decay, but we don't really have a good sense of what these deep function spaces are. What kinds of functions are in there? I mean, people have looked at the effects of depth, so everything that we know so far as a research community would apply there. But yeah, can we get a better sense of what these deep function spaces really are? What kinds of functions are in there? That's kind of an open problem. And the role of depth, and beyond what everybody knows about depth right now, we don't have anything more to add to that. But maybe this framework would give you a nice way to start thinking about from a functional point of view.
Thanks.
Yeah. There's something else over here, maybe. Yeah.
Learning about the population of the phi and psi matrix, are you like concatenating the feature correspond to every training data?
Yeah. So let me put that up here again. So the idea would be that I'm putting in, so I have n inputs. So I put in an input, and at this layer, somehow some pattern pops out at the output of each of the ReLUs. So there are n of those patterns. Those are the the fees there, phi 1 through phi n. And then after I apply the output weights, I'll have whatever's going into the next layer. I'm calling those the psi-i's. So for each input, I have a phi I and a psi I. Does that make sense? So they're kind of like what patterns they're showing up at these layers in the neural network. When you put in an input pattern, you get a pattern coming out of the neurons and you get a pattern going into the next layer of the neurons. That's what the phi and psi are here. Does that help? Yeah. They're basically just a representation of the data when you push it through your trained neural network at these different layers.
One more question. And we'll wrap up.
So I have many, but I get to meet with you later, so I'll just pick one. So
Okay.
you started out with a perceptron and you explained very clearly how the Tikhonov regularization becomes.
Yeah.
But then you started adding biases, you talked about CNN, and I can't do that in my head that all that generalizes. Is it trivial? Because of CNN, the weights are used so many places, right? So
Yeah, so yeah, let me just jump back. So I'll just say this. So let's just go back to maybe where was that picture? Yeah, let's just go back to this picture. So if anywhere in your neural network, you have a rectified linear unit that looks like this, it has some tunable input and output weights. It could appear anywhere, I mean, even in a convolutional layer. And as long as you're going to be also applying weight decay in training or tuning these weights, then at least if you trained and found a global minimum, which is another question, like, will we converge to a global minimum? If we, any global minima, then you'll end up with this kind of balancing condition.
if you have a bias inside there, you also apply.
So if you had a bias inside there, yeah, you could imagine that you augmented X with a 1 and kind of just absorb that into this. Yeah.
All right. So
Okay.
let's thank Rob again.
Good. Thanks. Yeah.
5 minutes till your next meeting.
Okay. I guess I have to start packing up.
So,
Okay.
Understanding of convolutional networks, you could think of the input patches of convolution as being.
Oh, hey.
one question.
Sure, yeah.
My question to ask me, but we were talking about depth. I mean, I think.
Yeah,
I also asked the same question, right? I mean, do you actually get a sense of the argument that they have?
No.
So.
Yeah, I mean, I don't, again, people have talked about like, certain functions can be represented much more easily with a little bit of depth. So we have those kinds of insights, but I don't have anything more to add based on this yet about how.
So you, multiplication of network itself, I think that doing well as compared to having the entire network. So
Yeah.
let's say that if you have less deep networks,
Yeah.
do you have a sense of saying that you have to have, they require more weights as compared to actually having a very deep network?
That could definitely happen. I mean, one example of a function where that happens for sure is like a pyramid function. So if you, and you probably have seen these examples, and there's a reasons for that like a 2-layer or a few layers will be very easy to represent a pyramid function, whereas a single layer won't be. So a single layer would not only need to perfectly represent a pyramid, it would essentially need an infinite width neural network, but it would also need infinitely large weights. Whereas if you go to 2 layers, then you can represent it not only with finite, but also finite weights too. So that's a little bit pathological, I would say, but it is true. So it definitely shows that there's going to be, exactly, yeah. And so, but beyond sort of that kind of, okay, that's true. I don't know, nothing that we've done so far.
So you just have to find up.
Thinking about what are these compositions of these Radon VB2 function spaces?
The integral is for like.
Inside, they're like, oh, what kinds of structure and low dimensional structures are sort of encouraged or fit nicely into these compositional spaces that don't fit so nicely.
Yeah.
But I.
Single functions. The pyramid is one example of such a function, but that there must be many other things too, and some characterization of that would be really nice.
I will coming too long.
Cool, yeah,
Did anyone else sign?
No, I think there's a couple other people like Peng, Yutong, they want to join. Is
Yeah,
it okay?
well,
Is it okay if they join?
yeah, no, that's good. I mean, I can also, I leave it because, I'm gonna go to dinner with Rob and want other people to have the chance to sign up.
Yeah, you just sound this computer. It's you.